Okay, good morning. Happy Monday. Our look at the calendar shows us that today is our last day of new material before our fourth quest. We'll have 5 quests altogether. Coming up on Wednesday is number 4. Today we cover quadratic models, that is to say word problems. Wednesday we'll take our quest. Friday we're doing problem solving, meaning more word problems. I just want to point out that the quest is on classes 24 to 30, which does not count today. Right, so the stuff from today, there aren't word problems on this coming test. Just 24 to 30, which starts with factoring trinomials and goes up through the quadratic formula that we did on Friday. Any questions on this schedule? Okay, so in terms of that quest, I asked you to open to page 59, which is where you'll find the sample quest problems for quest number 4. So they're there, and there are resources on Moodle and also on YouTube as usual, okay? So we begin officially on 61, but I just wanted to make sure we knew about the sample test problems in the packet. Okay, so let's go to the daily summary. Sam? Virginia, number 1. Oh, a little typo there. Thank you. Okay, so here's the idea. We're going to start with a square piece of cardboard demonstrated by this paper right here. We're going to cut out little squares from each of the corners. So for example, I could cut out these tiny little squares here. And then we're going to fold up the sides. 1, 2, 3, 1 more over here. Okay, so we make this kind of fat plus sign, and then we fold up the sides, and right before your very eyes, a three-dimensional object will appear. Don't even need the 3D glasses like the movie theater. There it is. So we see the box with no top. Thank you, Sam. Right. And so that's the box that I get if I cut out those little squares from each of the corners. And so what we want to do is think about, okay, we're going to cut out 4 inches from each of the sides. That's fine. Those are the sides of the little squares we cut out. And we want to make it so that the box actually holds exactly 100 cubic inches. Now this particular box right here, would you say it holds more or less than 100 cubic inches of stuff? It's a lot less, isn't it? Can you guys picture a cubic inch? It can be like this long on a side, but a cube. So can you fit 100 of these cube-sized things in here? No, not nearly 100. I've had many fewer in this thing. So what did I need to do at the start? Well, I needed a bigger piece of paper to start with. And of all the different sizes of paper I could have started with, we're going to find the one, or maybe more than one, that gives us exactly 100 cubic inches. All right? There you go. Thank you for clapping. That's yours. All right, so what we're going to do is start this problem with a variable. What's the thing that we have control over in this problem? How are we going to try to make a box with 100 cubic inches? It's the piece of paper, right? That's the only thing I have control over. I take a certain piece of paper, and then I cut out the 4-inch squares, and then I fold it up. So as soon as I have a piece of paper in my hand, I have no more control. I'm just following the process. So it seems like the variable should be the length of one side of my square. So how about we call this whole thing right here x? And then we're going to follow the process. But it is not enough to just label your diagram with an x. You have to actually define the variable. So let x equal. And there's a real big pet peeve that I have here is folks who let x equal something that isn't numerical in nature. Don't write this. I say let x equal one side of the square. That's not a numerical thing. It's not a number. I'm like describing a physical piece of paper here, and x needs to be a numerical thing, right? A quantity. So what is it? What are we measuring here in terms of x? It's the length or the height. You got to give me some word that indicates that there's a number happening here. And then we also have to include the units. So we'll say let x equal the length of the side of the square. Yeah, the original square piece of paper. That's what we're calling x. Yeah, that's it'll become a box once I cut out these 4 light pink things. But the original piece of paper is what I'm calling x. And then, like Sam points out, we also have to include units. Are we measuring the length of the side of the box in, miles? In inches, but you got to be clear what you're measuring, or what the units are in inches. So there's our variable. And now we need to come up with some formula. And I'll highlight here. We're looking to make it so that the box holds 100 cubic inches. What geometry word are we describing with that 100 cubic inches? That's the volume. So the volume is the formula that we need to sort of pull out of thin air. So what's the formula for the volume of a box? Normally it has 3 different dimensions. Length times width times height, right? That's the formula for the volume of a box. So length times width times height. Okay, so this is the formula we pull in. We know that this formula is true. And I'm going to highlight in yellow. And when they said 100 cubic inches, that's where we came up with the idea to think volume. They told us the volume was important. Sam?
And we already know the height, and we know that the length is height, right?
Okay, so let's start filling in. I think Sam wants to start replacing these letters with stuff that we know. So yeah, what is the height of the box? It's supposed to be 4 inches. So great, that last guy over here is a 4. That one's the easy one. And then we need to figure out what the length and the width are, not of the original square, but of the box. So I'll label here, this guy right here is what we're calling L, and this guy over here is what we're calling W. They're both the same, so it hardly matters. But can you guys figure out what those are equal to in terms of the original X? X minus 8.
Well, it's 2, but
yeah, each of them is going to be an x minus 8. Do we see that? That the length it's the original x minus the 2 4-inch pieces that we cut out on each side, right? So I'm going to highlight this guy in green as well, because that's one of the things that becomes a length of the box. So it's just the original x, subtract 4, subtract 4. So x minus 8 for both the length and the width. Okay, great. So now we've got our formula, which has only our variable x in it. And we're told what the volume is supposed to equal. What is it supposed to equal? 100, right? 100 cubic inches. That's what we want the volume to be. And so now we have an equation with just our variable x equals some number. And we're going to solve this equation. Okay, x minus 8, x minus 8. Can we distribute that through? Lobster claw or foil somehow. So this becomes x squared minus 8x minus another 8x plus 64. And then that times 4 is there at the end. Okay, so we'll combine the 2 terms in the middle. Minus 8x is minus 16x. Copy everything else. Okay, what next? Distribute the 4. That's a very natural thing to do, and it's not wrong. But if you distribute the 4, then you're going to have how many x squareds in the front? 4, which is way worse for me than the single 1 because I'm thinking I'm going to be factoring at some point in this problem, and I'd really much rather have x squared there than 4x squared. So what's another thing we could do with this 4 is divide by 4. We just divide both sides by 4. Not only does that avoid the 4x squared, but it makes everything smaller. And when you divide the left-hand side by 4, you did so for the sole purpose of crossing it off. It just disappears. So then our new equation, x squared minus 16x plus 64 equals 25. Okay, and now it's really starting to look familiar because they've spent time solving equations that look like this. What's the first step? Yeah, we need to get 0 on the right-hand side, right? That's one of our big steps for solving these kinds of equations. So let's subtract the 25 from both sides. At 39. Okay, and now we have two basic techniques for solving this equation. If we're lucky, in factors. If we're not so lucky, how do we solve it? Quadratic formula. Quadratic formula will solve any quadratic equation in the world. So we could always use the quadratic formula, but we spend time factoring because if the thing factors, it's often much quicker and more accurate to factor it than to use the quadratic formula. And just to be clear, in terms of this quest coming up on Wednesday, so I will ask you to use the quadratic formula once on this quest, and I will provide the quadratic formula for you, right? So you don't need to memorize it, although if you feel like breaking out in song during the quest to refresh your memory on it, that would be okay. But there is an entire page of solving quadratic equations where the instructions say in bold type at the top, do not use the quadratic formula on any of these problems. Because if I don't prevent you from doing that, then you could just do the quadratic formula all over the place and not show me any kind of understanding of like the easy factoring or the harder product sum factoring or anything like that, okay? So there will be a quadratic formula question, but there will be plenty where I say you cannot use that tool. Okay, so let's factor here. Feels like x and x in the front. Yeah, I think some people have already got it. We need a product of 39, a sum of negative 16. There aren't many things that go into 39. 3 and 13 happen to work. So we fill in 3 and 13. What about these signs? Yeah, got to be minuses to get that minus 16x and plus 39 when I multiply. Okay, almost done here. I'm going to write out this extra step. It's not mandatory, but I encourage you to really recognize this is what you are doing. Don't just memorize, oh, the answer is the opposite of the sign that's in the parentheses. You're setting each of these pieces equal to 0, and then you're solving much easier equations. Add 3 to both sides, add 13 to both sides. Okay, so we solved our equation. We got two solutions here, 3 and 13. We haven't really spent a lot of time this semester talking about like checking our answers. We've just solved equations and trusted that as long as we did everything correctly algebraically that the answers would work. But in this case, there's a problem. If you take, let's start with the 13. Let's actually imagine that this whole thing right here, x, is 13. Right? And so if I take away the two 4-inch pieces from either side, then how much is left here? Take away 4 and 4, it's 5 there, which means that this is also 5. So the dimensions of my box are 5 by 5 by 4. Yes, 5 by 5 by 4. 5 times 5 is 25, times 4 is 100. Okay, it works. Super. What if instead, oops, the left-hand side is the other answer? What was the other value of x? It's 3. And then we take off 4 and 4. And we say, well, this doesn't make sense, right? We don't have enough to take 4 off. We can't even take a single 4 off, let alone 2 4s. So x equals 3 just doesn't make sense in the context of the problem. Does it mean we made a mistake? No. Let's actually follow this to its illogical conclusion. Suppose you do subtract 4 and subtract 4. What do you get? -5, yes? So that means that this, even though it makes no sense, is -5, which means this guy also is -5, which means your dimensions are -5 by -5 by 4. And when you multiply those, what do you get? You get 100. So it's not that we did anything wrong. We solved an equation. We had 2 answers to the equation, but one of them doesn't make sense in the context of the problem. So x equals 3 gets rejected. So x equals 13 is our answer. Okay, as you are well aware, word problems are historically quite challenging, so the activity you should expect to be challenged on. Give it a shot and raise the flag if I can help.